Hi everyone and welcome back on the channel. Today I thought it would be nice to make a tutorial about how to make a cracked ice or cracked glass effect. In order to make this possible, we'll need to dive deep into the world of 3D noise as well as Raymarching. 3D noise will provide an endless, procedural cracks texture, while Raymarching will make possible to see through the material as if you could see the rifts from the inside. So as you can see, the Shadergraph to achieve this effect is really simple, but don't fool yourself. The Raymarching node there is where most of the rendering takes place. In fact, if you click on the wheel of the custom node, you will see that it comes from a HLSL file, and it is a specific function with a few inputs and one output. If you head into the file, you can see that it's composed of two main parts. The first part is the noise generator. It was originally written by Max Bitker, and I will put a link to his GitHub in the description below. I brought it to HLSL so that it's easier to work with in Unity. So basically, what we have there is a function that takes vector 3 in argument, so basically a point in space, and it returns a float 2, so vector 2. That contains both the Voronoi noise and the cracks from this noise. And basically what we're interested in are the cracks, but we will see that later. I created a simple Voronoi noise 3D float function. So the underscore float there is for the precision I want, and it basically calls the Voronoi noise 3D function we've seen. So I created a small subgraph that will call this Voronoi noise 3D function. So back into my Shadergraph, I temporarily unplugged all my previous nodes, and we will play a bit with the Voronoi noise 3D so that you can understand better how it works. So basically we're going to use our brand new subgraph, Voronoi noise 3D. So far you can see nothing, because we need a sampling coordinate. So we're going to put the position of the pixel that is actually rendered in space. And let's put object space. So as you can see, it's already displaying. If I put the cells on the albedo, you will see that it appears on the preview there. And it's already looking like broken glass. But another thing that is important to mention is that the brightest it is, the further it is from the closest edge. And this will be really useful for Raymarching later as a distance estimator, but we will come to it later. So how does Raymarching work? Let's take this blue line. It represents a 2D function. Where the line is blue, it means that the function is 1. Otherwise, it means that the function is 0. For instance, let's take a random point there. It has its own coordinate x and y, and as you can see, it's not on the blue line, thus its value is 0. Otherwise, the value will be 1. Let's now take into account the surface of the mesh. When rendering, Unity provides this green vector, meaning that you know the position of the camera, the distance from the camera, the view direction, and thus the position of the point you actually want to render. Let's check if this point matches the blue line. As you can see, it's not, so the value will give us 0. Then we want to loop over along the view direction until we match the blue line. To do that, we need a distance estimator. The simplest one we can think about is a constant value. Wherever you are, it will tell you you can go along the view axis from this constant value. So let's do this. Let's move along from the distance c there and see what happens. So as you can see, we're still not on the blue line, as the function will give us the value 0, and we need to repeat the process until we actually reach the blue line. But we're lucky this time. If we change the parameters, as you can see, we may miss the blue line, ending up in an infinite loop. And this is not what you want. So you may think, what if I take a smaller distance when calling my distance estimator. So, okay, you may never miss the blue line if you take small steps, but it will end up in a lot of loops, like a really high number, and that's not good. So luckily we have some Voronoi noise that provides us this yellow circle, meaning the closest point, the closest edge from our point. So as you can see, it touches the blue line at the bottom, but it's not exactly in our view direction. So after the first loop, we already are so close from the blue line, and as you can see, the distance estimator is way smaller, still touching the blue line. And after just 4 steps, we managed to reach our blue line, which is great. You need to keep in mind that every single pixel on your screen will need to go through that loop, so it needs to be as small as possible. Now it's time to put the theory in practice. So I created this Raymarch cracked glass function, and it will be exposed to shader graphs. So basically, as you could expect, it contains a for loop. Every iteration corresponds to a step further along the view axis. We keep in memory the current point, which is the actual step we are at. And basically in the main lines, we have this Voronoi noise computing at the position, and we estimate the value at this point, and we move the current point along the view axis, and we keep in memory the distance we traveled so far, and we reduce the output value as long as we go further and further. Whenever the value gets really low, it's useless to go further. Actually, it won't change the result at all, and it will just waste your processing power. The positive situation is when your value you estimated is above 0. It means you actually hit the rift. So it's time to return your intensity. So let's head back into our shader graph. We are going to remove the previous node we created to test the Voronoi noise, and we're going to test the Raymarching instead. Just make sure before starting that every argument matches the definition in the HLSL file. Otherwise, you will get the classic pink material. So now let's check out all the arguments we're providing to the custom function. The first one is surface point. It's actually really simple. We just choose object space or wall space for the position, depending on the value of a boolean that is exposed to the material. Later, we just scale the position and we give it that way. And all the others are just trivial. So basically, most of them are exposed as they are, so that you can play with it later in the material. And if we check what we have at that point, it's already looking awesome. This output is comparable with the scene depth buffer. So basically, the brightest it is, the less we marched through the material, and the darker it is, the more we traveled. So we can use this to lerp between a deep color and a rift color, and the result is awesome. So we can just connect this to the albedo. Also, I thought it would be nice to expose the smoothness to the user so that he can play with it. So basically it's just a vector 1, and I connect it to the smoothness. Now that we are back into the scene view, I just created 2 materials. They both inherit from the shader, but one is rejected and not the other. Let's start with the other. So I just put the material on the sphere there, and it looks great. As you can see, I have a few parameters to play with, such as the scale, the border thickness, so basically the rift thickness, the colors. So it's pretty nice, you have a lot of possibilities there, but I like to keep something bright for the rift and a bit darker for the deep color. So let's just keep it that way. Later, you have the purity. Basically, it controls the fading. It's pretty cool, especially if you want your class to have a certain thickness. This is the right parameter to move, but I will just leave it that way as well. It looks nice. Later, you have the smoothness. So basically, no trap here. That's just the smoothness. And the recursion depth. So right now it's set to 20, and as you can see, it's running smooth, considering that I have a screen recorder at the same time. If I put it to something lower, like 10, it will be a bit blurry. Basically, the distance estimator can go far enough and it can't really reach the rift. So it's close and it actually gives a pretty nice result already. In order to make it sharper without increasing the recursion depth, you can increase the border thickness instead. It will make a bit sharper and it will run like butter. But what if we put a really high recursion depth? Well, basically it will make it super sharp, and actually it's not that slow because most of the pixels we're rendering are returning before reaching 100. As we use 3D noise, you will be able to move your object and you will see the noise scrolling on it. This may be super useful for procedural generation, for example, but if it bothers you, you can still check local space. That way it won't move. And it won't move on rotation either. Now let's talk about the rejected material. As you can see, it looks more like ice instead of glass because all the rifts are all along the normal from the surface. So it looks great if you want to make an icy environment, and you can see the difference if I uncheck. Well, in my opinion, both look great, but just imagine having your procedural ice generation like this. It's super cool. I will end up this video by playing around with all the few parameters, so that you can see all the possibilities. A lot of things can be improved, and I can't wait to see what you guys did with it. If you enjoyed the video, please subscribe and leave a like. Also, if you're struggling with the tutorial, I will be glad to help you, so just leave a comment down below and I will reply. See you next time. Cheers.